Thank you for the introduction. Hi, everyone. Welcome to this talk. Today, I will talk about my research on security of heterogeneous systems and some research direction in this area for future. So I'd like to start my talk with introducing heterogeneous systems. Traditionally, computing systems were CPU-based. Basically, we had single-core or multi-core CPUs interconnected by on-chip bus or off-chip interconnect to the memory subsystem. So most computers had just one type of processor, which was CPU. But today, modern computing systems are all heterogeneous in every scale and in every environment, starting from our personal devices to cloud-based systems, HPC clusters. In these heterogeneous systems, in addition to CPUs, we have hardware accelerators. Accelerators are usually some parallel processors that can perform tasks very fast. So they can be general purpose application to accelerate a wide range of application, or some specialized accelerator for a specific task, for example, machine learning. Some of the examples of these accelerators are graphics processing units or GPUs, FPGAs, or ML accelerators. So in heterogeneous system, we have a combination of CPUs with accelerators, and together they can provide high performance and energy efficiency. And again, they are interconnected to the memory subsystem. So my research looked into security of these systems. Some of the well-known attacks in these computing systems are covert channel and side channel attacks. Now I will explain how a covert channel works. In covert channel, we have two malicious applications, spy and Trojan. So there is no direct channel between these two applications to communicate. So they build a covert channel through which they can communicate. And let's say we have a gallery app as a Trojan in our mobile device that has access to the photo but no access to the internet. We have another app, a weather app, that has access to the internet but no access to the photo. And there is no direct channel between these two based on the security policy of the system. So they can build a covert channel through which the Trojan can send the photo to the spy, and the spy can upload it to the internet. So we have information leakage here using this covert channel. A more dangerous attack is side channel attacks. In side channel, we have just one malicious application, and it tries to extract some secret information from a normal user of the system as a victim. For example, let's say we have a victim application that is running on the processor, and it is encrypting some plain text to the ciphertext. And it uses an encryption key, which is a secret information here. So while the processor is encrypting the victim's data, an attacker comes in and measures the execution time or the power consumption, or it can be electromagnetic traces on this processor. Then it analyzes the data that it collected, and he or she can recover the key, which was a secret information. In the context of microarchitectural attacks, covert channel and side channel can happen when we have co-location. Basically, when multiple applications from different users can run on the system the same shared hardware resources. So they use these shared hardware resources as a medium for creating covert channel and side channel. So co-location is the main requirement for these microarchitectural attacks. For example, cache can be a shared resource. Cache is used to speed up accessing to the memory in our systems. But now let's see how cache can play as a medium for side channel attack. Let's say we have a spy application that is running with the victim application both on the same core of the CPU. So L1 cache and L2 cache are shared between victim and attacker. First, the spy primes the cache. It brings up the whole data from the memory to the cache and fills the whole cache. Then it waits. Victim application do some memory accesses. So basically, the spy doesn't have any idea about the victim application. It just waits, and the victim application does its memory accesses. And it brings some data into the cache, evicts the spy data from the cache because the cache is shared, and brings its own data to the cache. Then The spy application probe the cache and measure the access time. For those addresses that has been accessed by the victim, the spy see higher latency. Because it is a cache miss, the data has been evicted from the cache, so it takes some more time to get the data from the memory. Based on this analysis, it can just find out which cache set has been accessed by the victim. And usually these accesses are correlated with the secret information, for example, encryption key. So by using this attack, the spy can get the encryption key, which is the secret information. Cache is just one example of these shared hardware resources. So in traditional CPU-based system, these types of attacks have been studied on a variety of resources, including so the functional units or the pipeline structures within the core, different levels of cache, L1, L2, L3 cache, the bus or interconnect, and also the memory. So these attacks have been widely studied on CPU-based system before. But how about accelerators? The main question here is that, do these accelerators add some security issues in our heterogeneous systems? In our past research, we focus on security of GPUs in heterogeneous system, graphics processing units. GPUs are everywhere. They are in our laptops and desktop to render what we see on the screen. They are also in cloud-based systems and HPC clusters to accelerate a wide range of applications. And some general purpose applications, including some critical ones, for example, self-driving cars, are also accelerated using GPUs. So there are some security concerns in all of these environments. For example, on cloud and clusters, multiple clients are using these cloud nodes, and they share these hardware resources. So it can lead to information leakage between the users. When GPU is used for rendering, it can expose some sensitive, some personal information from the users. Also, application with some sensitive data or algorithm are accelerated by GPU. So they can be compromised by any security issues or vulnerabilities in the GPUs. So security of GPUs are important in all of these domains. Now let's see how GPU works. CPU and GPU are both processors, and they have different architecture. So this difference in architecture makes them suitable for executing different tasks more efficiently. In CPU, we have a few cores, and it operates with higher speed clock. But on GPU, we have hundreds of thousands of cores, and it is operating with a lower speed clock. So usually the CPU is more efficient to perform some complex tasks, some complex operations on a small set of data. While the GPU has massive parallelism, it has massive multi-threading with all of these cores, it is designed to perform some simple operation on a large set of data in parallel. So GPUs are massively parallel. There are some SMs or streaming processors in GPU that share an L2 cache and global memory. And within the SM, we have some number of cores or execution units, register file, L1 cache, and shared memory. This is the overall architecture of a GPU. In terms of programming, as I mentioned earlier, GPUs are used for accelerating both graphics and computational workloads. On the computational side, the programming language for NVIDIA GPUs is called CUDA. And GPUs operates in SIMD or SIMD model, basically processing the same instruction by group of threads or working on a group of data in parallel. So let's say we have image processing application, and we program the GPU using some kernels. Kernel can be, each of these kernels can be just like applying a filter to all of those image pixels. So each kernel has a bunch of threads that are grouped in CTA or thread blocks. And they are further grouped in 32 threads called warp. 32 threads of each warp at the same time can be running on the GPU. And each of these threads is corresponded to one single pixel on the image to be processed for the image and being rendered on the screen. So this is how GPU works to give us massive parallelism. To study security of GPUs, our first question was that, is it possible to have covert channels on GPUs? We explored the feasibility of covert channel on GPU in some steps. The first step is to reverse engineer the scheduling and placement of application on GPU. Basically, when multiple applications are launched at the same time to the GPU, can be co-located on the same SM or on different SM. And then based on these co-location options, we can identify the shared hardware resources and we can build the covert channel on them. So for example, if the SPY and Trojan both are co-located on the same SM, then the shared resources would be execution units and L1 cache. But if they are located on different SMs, we can still have this covert channel using shared L2 cache and global memory across the SMs. So we built a covert channel in all of these resources, but here I just explained one example of it on L1 cache. So L1 cache on GPU has 8 sets. So SPY and Trojan pre-agree on 2 sets for handshaking or synchronization before the real communication. First, the Trojan sent, I'm ready to send signal to the SPY using a cache set. And once the SPY receives the signal, it acknowledges by sending a ready to receive signal to the Trojan using a different set, a second set. And then by receiving this signal, the Trojan can start the real communication. And thanks to GPU parallelism, it can launch parallel threads, 6 parallel threads to send 6 bits through different cache sets at the same time. So we have used this GPU parallelism to increase the bandwidth of our attack. And in another level of parallelism, we can have one instance of this covert communication on each SM of the GPU independently. So we can increase the bandwidth by n time. N is the number of SMs in GPU. As an example, in Volta GPU, we have 80 SMs. So potentially, we can increase the bandwidth of this channel by 80 times. At the end, by having this GPU unique architecture and parallelism, we could build covert channel with a bandwidth of over 20 megabits per second on Volta GPU, which was the fastest known microarchitectural covert channel under realistic conditions. So it means that on GPU, we can have very high quality and bandwidth covert channels. The next question is that, can we have more dangerous attacks like side channel attacks to extract some sensitive information from a victim application on the GPU? And we explored different scenarios and developed several side channel attacks on GPU. One of these scenarios is just spying on a graphics application. So when GPU is used for a screen rendering, we can launch a spy application to extract some secret information from this rendering process. The first attack that we developed was website fingerprinting. Current browsers are all using GPUs to accelerate the rendering process of web content. So when a user is browsing on the web content are first uploaded to the GPU memory, and it is being processed by the GPU and being rendered on the screen. We found that by tracking the GPU memory utilization, we can find out which website the user has visited. So we can get a time series of these memory allocation trays on the GPU, which tells us how the victim is using the GPU memory. And these traces are dependent to the website content. Basically, how many objects need to be rendered, what is the size of each object, and something like that. So for example, here you can see that these are the traces, the memory allocation traces on GPU when the victim is visiting Google, Facebook, and Amazon website. You can see that each website leaves a unique trace on the GPU memory allocation trace. So we collected this data for 200 Alexa top websites. We trained a machine learning-based classifier, and we could get the accuracy of more than 90% for 200 Alexa top websites. Another attack was tracking user activities when the user is just using these web browsers, using the inter-keystroke timing. So when a user is typing her or his password in the Facebook password bar, we wanted to see if we can get the password or the number of characters of the victim password or not. So we can track the memory allocation and also record the time of each of these allocations. So this plot shows the time intervals between every 2 consecutive memory allocation on the GPU. So when no key is pressed, the screen should be re-rendered at a fixed rate every 600 milliseconds. And once a key is pressed, the screen should be re-rendered. So we have a decrease in this time interval. So you can see that we have 6 dips in this plot, meaning that the user has typed a 6-character password. And then by using some correlation analysis on users' typing pattern and this time inter-keystroke timing, we can get what was the exact key that the user has typed. So, so far we have seen that GPUs are vulnerable to covert channel and side channel attacks, but the next question is that how we can design secure GPUs. All modern GPUs support this multi-programming, so just to improve the performance of GPU. But we have seen that this multi-programming can lead to information leakage through covert channel and side channel attacks. So the challenge here is that how we can efficiently run multiple applications concurrently on the GPU to fully utilize the GPU resources and at the same time protect against these types of attacks. So there's a trade-off between security and performance. There are 2 straightforward solutions to make GPUs more secure. We can have temporal partitioning of application, meaning that in each time slot, one application can run and then it is preempted and GPU context switch to another application for the next time slot. So this approach is the best approach for security because in a given time, there is just one application running and there is no shared hardware resources. But just the thing is that it is not a good approach for the performance because one single application usually cannot utilize all of the hardware resources. So we have underutilization here. Another straightforward solution is spatial partitioning. Basically, we can assign different kernels, spy and Trojan, to a different subset of SMs on the GPU. So they cannot share the Intra-SM resources, but they can still create these covert channels through L2 cache and global memory that are shared across SMs. So this approach cannot completely protect against these covert channels. To protect against these types of attacks, we propose GPUGuard. GPUGuard is a fine-grained Intra-SM resource sharing in a secure way. So we have 2 main components here in the GPUGuard. The first component is detection, and then we have defense. In the detection component of this GPUGuard, when multiple applications are running on the GPU, we just monitor the resource utilization across applications through a set of metrics, for example, hardware performance counters, how the cache is being utilized, how functional units are being utilized. So we collect all of these events or architectural events, and we use machine learning classifiers to just detect the attack, basically detect the existence of any contention on these resources. So we can classify application as a normal application or an attack. And if it is an attack, in both of those resources, they are building the attack. For example, if it is a cache attack or functional unit attack. And then when the attack is identified or detected, the second component of our design just isolate the contending kernels. For example, if it detects that these 2 applications are creating contention on the same hardware resource, it is a possibility of covert channel and side channel. So we isolate them into different security domains. And these security domains depends on the resource that they are creating contention on. So we have a hierarchy of this isolation at different levels. For example, if it is an attack on the functional unit, we apply this data path slicing, so making sure that each application is using a partition of these resources in the GPU pipeline, in the GPU core structure. And if it is a L1 cache attack, we can just have bypassing the cache or repurposing the cache to make sure that these two cannot have any interference on the shared hardware resource. So by having this GPU-Guard, we try to have high performance by having multiple applications still running on the same SM of the GPU. But when there is an attack, we just try to trigger the defense to isolate the application. So we can minimize this performance impact of our defense. So far, I talked about security of discrete GPUs. Basically, in discrete GPUs, we have a separate memory for GPU, and the GPU is connected through the PCIe bus to the CPU chip. But in personal devices, we have integrated GPU. For example, in our smartphones, we have just one single chip, and CPU and GPU are integrated tightly in the same chip, and they share the system memory like this. So in our current project that is funded by NSF, we are looking into security of this integrated CPU-GPU system. And this is a common architecture for desktop, for laptops, and mobile and IoT devices. For example, every Intel-based system has an integrated GPU on the same chip. This is the architecture of an Intel-based CPU-GPU system. So these are CPU cores, and we have integrated GPU. Both of these two processors are sharing this interconnect, the last level cache, memory controller, and system agent. So in these types of architecture, a malicious application can just run on the GPU, and it can spy on the application that is running on the CPU using these shared hardware resources. And again, through the microarchitectural covert channel and side channel attacks. So we call it as cross-component attacks. So one malicious application is running on GPU, another one is running on the CPU. So they can communicate secretly, or one of them can extract some secret information from another one. We developed some of these cross-component attacks on Intel-based systems using different resources. The first one was a last-level cache. Basically, a GPU and CPU can covertly communicate through this last-level cache. And another one was through the contention on the ring bus or the interconnect, the on-chip interconnect that connect CPU and GPU to the rest of the system. In these types of cross-component attacks, we have some new challenges to overcome. The first challenge is that these two processors have asymmetric view of the shared resource. For example, if they are targeting this last level cache for attack, each of the CPU and GPU, they have their own memory hierarchy. For example, on GPU, we have this L1 and L2 cache private to the GPU, and they are used just for graphics application. We have another cache that is just for both graphics and computational stack. And on CPU, we have another hierarchy of memory. We have L1 and L2 private to the CPU cores. So to make sure that all of our accesses reach to this last level cache, we need to reverse engineer all of this hierarchy, because the details of this architecture are usually not documented by companies. So we need to reverse engineer this hierarchy and make sure that all of our accesses reach to these shared resources to create the attack on that. Another challenge is the frequency disparity between different processors. CPU and GPU operates with different clock rate. So to build this communication between these two processors with different clock rate, we need to synchronize the communication. And one of the approaches to overcome this challenge was just using the GPU parallelism to make the attack faster to keep up with the speed of the CPU for communication. Another main challenge was lack of timing on GPU. In GPU programming APIs, for example, OpenCL or for the graphics OpenGL, they do not provide any timing interface. And we have seen that for these types of attacks, we need timer to measure the access time to the shared resource. So we need to build our customized timer using the GPU hardware resources to make sure that we are able to measure the access time to the shared resource to encode the information in the covert communication. So these are some of the main challenges in this new environment to build cross-component attacks, the attacks that span different components in the system. By overcoming these challenges, we could build a Covert channel between CPU and GPU in Intel-based SoC with the bandwidth of 120 kilobits per second, and the error rate was 2% for this case, GPU to CPU. The attack that I just explained was an attack on native code, basically using the OpenCL as a programming APIs for Intel-based systems. We could build this attack, but these types of attacks can be more dangerous. They can be launched remotely in JavaScript. So there are some works that implement these types of attacks on CPU-based system in JavaScript. So the attacker just launched an attack in JavaScript, and it gets launched on the CPU hardware resources, and, for example, implement the cache-based attack. But for defending against these attacks, major browsers just disabled the timer, or they limited the precision of the timer. So these types of attacks is not possible anymore in the remote setup in JavaScript. But to accelerate the web rendering, most of these browsers are going to support GPU-based APIs, for example, WebGPU. WebGPU is an emerging API to support this GPU acceleration on the web. So by having these new emerging APIs, we can launch our attack on integrated GPU, and using these shared resources, we can spy on any application running on the CPU. So basically, we can launch these cross-component attacks remotely through the JavaScript and these new APIs in JavaScript. So here's the threat model. The attacker can design a malicious website. The user just visit the website, and the attack, actually using the web GPU, it gets launched on the GPU, and through these shared hardware resources, it can spy on any application that is running on the CPU. These are some traces that we collected as our preliminary result in this area. Basically, when the user is visiting different websites, the spy application can just access the LLC through this threat model and measure the access time. So these are the access time on different sets of LLC when the victim is visiting CNN, Oracle, and Wikipedia. So you can see that we have, again, unique traces for each website, and for different trial of the same website, they look similar. And of course, for these types of attacks, these cross-component attacks, we also need to design some defense mechanisms. Defense mechanism for these types of attack can be designed at different levels of software and hardware. It can be designed in JavaScript, and basically by limiting the permission models in JavaScript when they are using these APIs. It can be designed in the GPU driver level to isolate the GPU application from CPU applications, and any memory that is dedicated to GPU memory from the CPU memory. Or it can be at the level of hardware or microarchitecture, basically by partitioning the resource for two different processors. For example, a subset of LLC last level cache can be just dedicated to GPU processes, and another subset can be dedicated to CPU processes. So I talked about my past and current research in this area, but now I would like to talk about some future research direction in security of heterogeneous systems. So far, my research has focused on security of GPU-based systems, either discrete GPU or integrated GPUs. But GPUs are really just one instance of these types of accelerators in our systems. We have a variety of accelerators with different architectures, and they are connected to different bus architecture, and the memory also is heterogeneous. We have different memory technologies and memory designs and architectures today in our systems. So any of these types of architecture can lead to some novel attacks. We have all of these different innovation in all of these layers of the hardware, And in every environment, and it has its own security challenges. For example, in desktop and laptop, the security challenges are different than the clouds or HPC clusters. So we need to study all of these threat models in different environments for this security, for these heterogeneous systems. More specifically, for example, in end-user devices, we have seen that we can have these types of cross-component attacks between CPU and GPU. But in these systems, we also have some other accelerators, for example, FPGAs, or some new accelerators called NPUs, neural processing units. They are also integrated on the same chip as CPU, and they are running some specific application, for example, ML-based application. So they can potentially open up some new context for these microarchitectural attacks. In terms of the memory subsystem, we also have some new paradigm, for example, processing in memory. Basically, we have a 3D stack of the layers of the memory. In some layers, we have computational units, and in some layers, we have just storage. So we do the computation near where the data is stored. So we can just remove the data movement between CPU and memory. By removing this data movement, we can increase the performance, of course, but it can also increase the security of systems in some ways. For example, there will not be any attacks on bus or interconnect. When the data is coming from CPU to the memory, we have some types of attacks on the bus to get the information about the data. But in these types of architectures, there is no possibility of those bus-based attacks. But it can also introduce some new attacks. For example, one of the possibility here is that these computational units in processing in memory, they are shared for different applications. Basically, there is no types of isolation between different applications running on the system. So one possibility of attacks would be through this computational unit in the logical layer of this 3D stack memory. And another possibility would be row hammer attacks. Row hammer is when a process is running different rows of the DRAM. It can induce, so if it accesses very frequently, it can induce some bit flips or fault in the adjacent rows. So it is called as bit flips through the row hammer attack. So for these types of processing in memory, we need to activate and deactivate the memory rows very frequently to do the computation. And these frequent activating and deactivation, it can lead to row hammer attacks. It can flip some bits in the adjacent rows of the memory. So it can increase the possibility of this fault injection in the memory subsystem. Another direction is just in larger scale systems, for example, in high performance computing clusters, we have a huge number of accelerators and processors that are interconnected to just give us significant performance. For example, NVIDIA has some of these multi-GPU systems, DGX1 and DGX2. They are already employed in HPC clusters in national labs. These are usually used for accelerating applications like deep neural network. When we have very large model or very large data set, so the model or data set are distributed over all of these GPU memories, and we can have GPU to GPU communication in these systems to just make a large application happen and being accelerated on these systems. In our preliminary results, we have explored the GPU to GPU attacks in this box, in these multi-GPU boxes, in collaboration with the national lab. For example, here we have, let's say we have a process on GPU 0 and another process on GPU 1. These are two separate isolated processes. And the process that is running on this GPU can just get access remotely to the memory of this GPU. In these systems, we can have remote access to the memory. And access to the memory is isolated, but the thing is that these microarchitectural resources, for example, this cache is shared. So we can use these types of microarchitectural shared resources to build our covert communication. For example, this is an example of a hello message sent from a process running here to another process running here in a DGX1 box. These types of attacks are really dangerous because these types of multi-GPU boxes are already deployed in national labs and for some critical applications. In cloud-based systems, there is a trend to accelerate this deep neural network using the GPUs or AI accelerators. And both hardware and software are evolving to just support this trend. For example, we have TPU or tensor processing units from Google that is specific accelerators for just CNN application. Or we have some specialized core in NVIDIA GPUs, they are called as tensor cores, to do just this DNN operation very efficiently and very fast. So with these novel technologies in both hardware and software, some types of new microarchitectural attacks can happen. Some example of this can be just a model extraction attack. For example, using these microarchitectural covert and side channel, we can get the hyperparameter of the models, which is a secret information for more companies. And of course, we need some mitigation at different levels here. For example, we need to make sure that the architecture of these accelerators are secure enough against these types of attacks when we are designing these new accelerators. We need to make sure that when they are shared in cloud nodes and in multi-tenant environment, they are securely shared. So we don't have any information leakage across different clients of the same cloud. And also when we are scheduling the task from different clients, they also need to make sure that they are also securely scheduled on the same shared hardware resources. So as a conclusion, we have seen that heterogeneous systems are actually evolving in different aspects, in different environments. We have these systems in every domain right now in critical types of applications. And usually they are designed for giving us more performance and energy efficiency. And the security of these modern systems has received very little attention so far. We need to investigate all of these threat models and actually make sure that we have secure execution on every processor. We have secure integration of these processors with the memory. And also we securely share these resources between different clients or different users of the same system. With all of this innovation, the attack surface is expanding, and as a result, we need some new trust models, new security defense mechanisms to close any possibility of these types of attacks on the shared hardware resources. And thank you so much. I'll be happy to take any question.